Okay. So, okay, let me see if this one works now. Okay, that's great. So interactive robotics. So in the lab, we work from application standpoint, we work on both robots that interact with humans and robots that interact with the environment. And from methodology standpoint, we work on both low-level design modeling of such robots and also on the higher level learning and control of these interactions. So certainly this created this interesting project here. And so specifically for our human-robot interaction on the low-level design side, we have been working on a class of inflatable soft robots that can provide support to human joint, as you can see for the knee joint in particular. And we also designed these soft robotic manipulator that can assist and augment human capabilities. On a higher level, we primarily look into game theoretical approach to model human-robot interaction. That's some of the things we're going to talk about. Specifically, we focus on looking at how human and robot interact with each other when they do not really know each other's intent. So we develop a lot of game theoretical models on that. We also conduct a lot of human studies to really fit the human models. So on the robot environment interaction side, on the low level, we work a lot on designing these with mechanical compliance and these drones that can physically interact with the environment, as you can see in these pictures. And I'll also share a little bit more about these work today. But on the higher level, we also work on control planning and especially looking into how we leverage these collisions to generate agile flight behaviors, let these drones autonomously fly through narrow openings, et cetera, et cetera. Apparently, it's a there are a lot of topics that we can possibly cover, but in the interest of time, I decided I would look into the lower level, relatively lower level work on robot environment interaction, focusing on flexible aero robots and a little bit on our game theoretical modeling for human-robot interactions. So our work on robot environment interaction aims to answer this question: how to sustain and harness collisions with the environment. So we specifically work on this area of aerial robots, drones, UAVs. So I don't really think we need a lot of motivation on why aerial robots are useful. You can see many of you probably have a DJI drone just for fun, right? So, and they have been widely used. And as you can see in all these applications, these robots are far away from the environment. And people usually talk about what? Collision avoidance, right? So, but what I would like to argue here is that oftentimes it is very difficult for you to guarantee such collision avoidance. For example, in agriculture, in search and rescue, in scientific discovery, where the environments are cluttered and where there are a lot of uncertainties in the environment, it's very difficult or it is very costly to completely avoid collisions. And there are also other applications where your goal is not to avoid collision. For example, when you're trying to put some sensors on these civil infrastructure with an aerial robot, the robot and the environment will physically interact. So how do you really enable robots to physically interact with the environment when needed? And there are certainly things that people can do on the perception side, on the control side. But the first question we will ask is there any benefit to add compliance, mechanical compliance into aerial robot design? Or what are some of the new capabilities that will enable? So that leads to our work on flexible aerial robots. And then I briefly, separate that into three parts. I want to first give an overview of different aerial robot design we have. And I want to dive deeper into a passive quad rotor that we have that we call Squeeze or Explorer, and another soft quad rotor we call that Soba. Very quickly, an overview. So I want to first acknowledge that there are a lot of work going on in the flexible aerial robots, one of the most exciting area in aerial robot field. But in our lab over the years, we have worked on active foldable robot drones that can actively change their morphology and fold itself. And we have worked on passive foldable drones, which means these drones will be folded when they contact the environment. We have worked on soft inflatable drones that have inflatable chassis and have almost continuous adjustable stiffness of the drone stiffness of the chassis. And we also have worked on whole body perching drone, where the body of the drone, the chassis itself, can also be used as a grasper. So we have done a lot of different design work, but today I want to focus on this passive foldable drone and the soft inflatable drone to demonstrate their capabilities in physical interaction with the environment. So Squeeze, we want to start with that passive foldable drone. So this work was led by my student Pershma, my former student Pershma, he has graduated. And so the idea of this Squeeze drone is fairly simple. So we add a torsional spring, and that torsional spring connects the middle piece of the drone, and then also the the rotor, right? So, and then what happens is that when you, for example, when you use your hand to pull the drone, or when the drone flies forward and it get contact by the environment, what's going to happen? The chassis will be folded, right? So, and this foldable drone also generates a lot of challenges involving control. As you can easily tell, here just provide a general overview. The challenges are mainly twofold. So for those of you that work on drones, this is probably the most standard dynamics that probably many of you have seen in textbook and papers, that to describe the translational dynamics and these to describe the rotational dynamics. What's different? When the arm of the drone is folded, the first thing that changes is the moment of inertia of the drone. Right? The second thing that changes is basically what we usually call control allocation matrix. That means when the geometry of the drone changes with the same rotor speed, you're going to generate different momentum. Although the total force and thrust is the same, but the moment is going to be different as your drone changes to a different morphology. So that generates a lot of challenges in how do you really run online estimation of the drone's physical parameter, and how can you do adaptive control on that. And we have a paper on that to look into low-level additive control to guarantee stability. And well, I'm not going to dive into details here, but for those of you that are interested, I'll be happy to talk more. So once we have like the low-level adaptive control and stability guaranteed, so the next step is to look into admittance control. So this drone that we designed is for traversing in very narrow openings like this one, right? So then certainly what we need to focus on is to look into admittance, right? So when you fly into these narrow openings, the yaw of the drone is going to be passively changed, right, by the environment. And what you don't want is the drone's controller to fight with the environment, right, and bring the yaw back. And then because, as you know, at some point, your drone is going to be saturated and it will crash, right? So this is a very simple admittance controller that we designed. And then just very quickly showing you that some simulation result in both small openings and long passageways. What we have shown through this quick simulation is that, with this, second order admittance controller, the desired yaw, which is the set point for the yaw angle for the drone, is able to basically follow the yaw angle, because as we know, the drone is going to be sort of pushed back and forth by the environment, and you design the set point that admit that disturbance instead of fighting this, right? So that's the general idea. I want to quickly dive into experimental results so you can see how the drone operates, right? So the arm can be like passively folded. And then this is just a recap of the structure at the higher level, lower level. And quickly, we want to show you drone flying through a gap that is narrower than its original width, right? And as you know, for the regular design, the drone is going to get stuck and crash. But here, what you are seeing is that when the drone contacts the environment generates a yaw disturbance, and the drone admits to that disturbance, as you can see here, and then fly through these passageways, right? And we have very high success rate. We never really have any crashes. Here goes the passageway, right? It's a little bit more tricky because the disturbance is more persistent along the way. And what we're seeing here is that, again, through admittance control, the drone continues to adjust the set point and then admit the disturbance, and then what we say, squeeze out, right? So this is the drone at the beginning, and as you can tell, it yaw, and then admit to that yaw, and then when it goes out of the passageway, it retains its stability. So this is some interesting initial work we did on this passive foldable quad rotor. And that really motivated us to think about, okay, what are some of the additional benefits of having foldable chassis? Or more broadly speaking, what are some of the benefits when the drone can physically interact with the environment instead of waiting? So we start brainstorming. There are a lot of things that we can possibly achieve with the foldable chassis. We have show flies and squeeze and fly through narrow openings, but we certainly can expect improved disturbance rejection because of the compliance. The drone can start pushing an object to forceful motion. And we can also potentially explore contact-based exploration and mapping, which means the drone can basically slide along the wall and create a mapping of the environment, right? The inspiration comes from, there was one day that we ran out of power. And then students can steal and can basically just push their way out by just touching the wall, right? They don't really need to see anything. And we're like, okay, so can the drone do that if the drone can also contact the environment? And lastly, we would also want to explore, can we really generate any agile flight behaviors with these foldable drones through collision? Instead of avoiding collision, if we do collision inclusive or collision aware trajectory planning, what are some of the new capabilities these drones will have? So let's dive into these. The one that I kind of voted are the ones we're going to highlight a little bit more here, but we have a paper there that shows other capabilities. So basically, this new version called Explorer. It's a similar design, but in this case, we make these two being foldable instead of like the one that is like on the opposite side. So all these capabilities that we talked about earlier was enabled by what we call wrench estimation, because everything that you're trying to do through contact is built upon your understanding with the environment, which is wrench estimation, right? Every time when you're drone, you fly, when you contact the environment, you got to figure out how much interaction force, interaction torque is there for you to potentially reason about that and generate, and then basically do planning to control the decision making. And then after that, we show that the drone can do exploration, can do mapping, and can do what we call swift navigation. So here is just a block diagram. I know we're at Icon and everybody likes block diagrams. So here's a block diagram of the overall system. And so we're going to start with this block, which talks about wrench estimation. The question is, I have IMU on board, and I know at some point my drone is going to contact the wall. The question is, when does it happen? And when it happens, how large is the interaction force, right? That's the problem statement. So again, we go back to this Explorer dynamics. The only difference is that now you're expecting an external force as a disturbance force and external force as a disturbance force. So for this particular we limit ourselves to just estimate the disturbance force because we basically assume that the force is mostly on the perpendicular direction. So we do not assume there is a rotational torque, but still, that's something we can also do using the same wrench estimation algorithm. So the interesting thing for wrench estimation for the drone is that you can do wrench estimation at different locations. For example, we have IMU sensor of each of the propeller guard to be specific, and then we can run wrench estimation there, right? So because we have the IMU, we can know how much the arm is rotating. Then we know, because this is generated from external force, then using the IMU readings, theta dot, theta double dot, you can estimate how large the interaction force is here in this plane, right? In this propeller plane. And so we pass that through a low pass filter because everybody knows, IMU is noisy, so you probably don't want to use a raw data, especially when you're double differentiating. And then we have a wrench estimation at the arm, right? And then of course, this one is done through rotation matrices. You basically transform the force from this frame to the body frame and from the body frame to the board frame, right? Through rotation matrices. The interesting thing is that you can also run wrench estimation at the center, at the CUM of the drone. And then for those of you who play these quad rotors, there is a high-end IMU in the flight controller. We use a PX4 flight controller. There is an IMU there that is relatively higher quality, less noisy, etc. And then we know you can similar running that using the dynamic model here, right? Because there is that equation here, and there is a very simple rewriting of this one. And certainly there are issues, right? So what we have observed is that you can run wrench estimation at the arm, and then generally it has very fast convergence, which means the moment you have these forces, it takes less time for the wrench estimation to converge to a steady state and for you to know exactly how much the force is. But on the other hand, the wrench estimation at the center of mass can really quickly identify the wrench, which means it allows you to get better timing. It allows you to know what happens. This allows you to know how large the force is, right? So certainly there is a trade-off here. You can see this one has fast convergence, but the estimated wrench is often attenuated because of the low pass filter we have, right? And then here, the wrench estimation at the CUM has that peak wrench because we don't need to run like crazy filtering because of the high quality IMU, but it's generally slow. The reason is because the force needs to be transmitted from the arm to the center of mass, right? And then that is where the delay happens. So naturally, you can fuse these two. And this is basically an algorithm we have here, but the essence here, the idea here is this. When the drone is not in contact with the environment, then we purely trust this one because we know whatever we get here, probably noise anyways, right? So you're not in contact, you probably shouldn't get anything here. But when there is a contact, right? And then the wrench estimation from here changes very fast, okay? Then we use that because we really want to make sure we know the timing. The moment it happens, we want to use that and identify when that happens. And then when the rate of change is low, that's when we know that the contact is becoming more of like steady state. And then we tend to trust more on this one to help us figure out what is exactly that value fast. Right? So that's the overall idea. And of course, there are tuning parameters you can see, but that's something that we're doing by leveraging the sensors on both the arm and the center. And then as you know, the reason behind this, guys, is because right now it is not a single body, right? It's a multi-body system. You have the centerpiece from here, and you also have like multiple body, and then so you can run these wrench estimation in a different body, and that allows you to do this sensor fusion. Certainly, I can't do that when you have like a conventional field, but everything is supposed to measure the same thing.
So do you have a time use for one context versus two context?
That's a great question. Yeah, that's a great question. I think for many of the things that we are doing here, so we usually assume you at the most have two. So we do have two, and then of course I think maybe there was an equation somewhere. I think maybe here, right? So we do add all the forces from all the four, and typically you can. It's very rarely you have four of them contacting at the same time. So at most in our experiment, we had two in contact, and we add them all together, and we use that to compare with the one we have assumed. Yeah. Okay, so let's very quickly see some results, right? So we have a load cell mounted on the wall, and we have a drone that is pushing this object, right? I think I kind of skipped the video, but you can see that's what happens when the drone pushes this object. When it goes to here, then this load cell is going to have a force reading, right? And that force reading is essentially what we apply to the wall. We basically command the drone to apply 2 Newton force on the wall, right? So what happened is that we run all these wrench estimation algorithm. There's a lot of figures here, but there's a lot of lines here, but I want you to focus on all these ones that have X here, because our force is in the X direction. Okay, so what we'd like to highlight is that the center of mass-based force estimate converts very slowly. The center of mass-based wrench estimation is this line. And as you can see here, when the force is being applied, it takes a while to converge. And that can be also highlighted in the zoom in figure. That's the wrench estimation based on center of mass, right? Even at the end here of this plot, it still doesn't converge yet. On the other hand, the arm-based force estimate has a lower peak. This is the arm-based wrench estimate. It converges very fast. It doesn't overshoot that much, again, because of we are just really running that at the flexible body here. It doesn't really have that long convergence, but as you can see, it's very difficult to figure out when that contact actually happens by looking at this graph, right? So we basically run a sensor fusion, and this is the line that we get. I think Becky has yeah.
Maybe I can add.
Okay.
Yeah.
Okay. Okay. Sounds good. So this one gives us a rough estimation of so how accurate our force estimation is, and then as you can tell, I'm not gonna lie, this is not super accurate, and then there are a lot of reasons. I think we can enumerate a lot of these. Model is not perfect. IMU is not perfect. Sensor fusion is not perfect, right? So and at the end of the day, we have friction here, right? So a lot of things are not perfect, but what we're trying to see is that at least we're able to convert to a value that is close enough to what we're trying to apply, and we can potentially start using this information to do something more. And I just want to highlight, these are the few lines. This is an original figure, and this is zoom. Okay. So we're like, okay, so now we have a wrench estimation, which means in real time, I know how much force is being applied to my joint. So what can we really do with it, right? The first thing we started is to look at, can you do contact-based mapping or contact-based navigation? We started with contact-based navigation or exploration, right? So we basically designed the drone's new locomotion mode. For example, we start with saying, okay, how about we generate a new mode called exploration? And then the exploration mode is pretty much the standard one, which means when the yaw rate and the external force are both small. What does it tell you? It tells you the drone is not really in contact with the environment, right? So, and then in this case, then we do not really need to do anything. And then basically we just for example, in this case, we just command the drone to continue going until it hits the environment. Now, when the drone contacts the environment, okay, so that the condition to look at this state is when the yaw rate is small, but the external force is large. What does it mean? It means that I'm not really yawing, but here's a big contact force. It means I start touching the wall. In that case, guys, what we generate is a new locomotion mode called sliding, right? What we do is if you have force in X direction here, then I would just command you to go Y direction, such that you can slide against the wall, right? And that's what happens. And I think later you're going to see another video on that. And then the next one is tactile turning, because in situations like that, you do need to turn. And in this case, what's going to happen? Your yaw estimate is going to be very large, right? Because when you go from here to here, your drone is going to quickly turn, and then you realize, oh, probably I'm at a corner, right? And in this case, we basically update the yaw set point such that the drone continues to rotating until it hit and go back to the tactile traversal state again. Okay, so what can we really do with it, right? So of course you can do contact-based mapping, but contact-based navigation. But for mapping, we also realize there is a cool application here that you can basically slide against the wall here and generate a map, right? And that's actually what we did. And I just want to fast forward to a video. The drone flies in, this is exploration mode, and then it contact start traversal. This is all autonomous, right? And start traversal, and this is all based on the wrench estimate and then the yaw estimate. So we know, okay, the drone is yawing here, and then at that time the wrench estimation is in this direction, so I command the drone to go here, right? So originally the wrench estimation is in this direction, so it go perpendicular, and now it goes in again perpendicular direction. Here's a yaw, and then the finish, and that's the map it generates, right? So similarly, you can do the same thing for another shape. And this one, the challenge is that it has a lot of turning, right? So we have to generate a lot of, we have to enter that tactile turning mode a lot. And you can see we again continue to reach utilizing the yaw estimate and the wrench estimate. So the drone will literally, fly autonomously through this environment and complete the mapping. Okay, so it continues going, and then another turning. And I go back to traversal because the yaw really small. Again, turning, and then traverse again. And then of course turn again, and that's becoming. Of course, right now this looks a little tilted. It was because my student when he plotted, he didn't really align the frame very well. So my apologies for that. But you can see it matches quite well. And in the paper we show that we have the dimension that we get from the drone from this mapping is plus 5% of the actual dimension of this real environment, right? So you can get that done without really relying on it.
Not the screen doesn't.
This is what we call that explorer. It's the same idea. You still have the torsional spring. The only difference is that there are two differences. One is that the spring stiffness is slightly higher in this case, but that it doesn't really bend like crazy. But and also on the other hand, we mostly designed to have these two propeller or these two arms to be foldable because we're expecting that kind of slide around. While the other one is mostly designed to be like squeezing and flies.
You have the spring model and the spring system in the.
Yes, we do have that, and it's I can talk with you more, on that for sure. Yes.
Is the drone always trying to go to the left? Let's say, like, why would you go to like that in the edge?
Why? And the reason is because, for example, if you continue going like this, right, and in this particular direction, the wrench estimate will change. The wrench estimate, for example, here, the wrench estimation is in that direction. But when it goes to here, let's say one propeller is here, the other one is not, then the wrench estimation will be in that direction. It will turn. Right. And then as they continue going, the wrench estimation will be continuing to update it. And of course, one is here and again.
It's like it's constantly inserting a force towards the wall.
It's always contacting the environment. That's how you know, okay, where I am, and then you know what to do next. Right. All right. So we're happy with mapping. So what can we do next, right? So with that contact, we also started thinking, okay, now I know my drone can collide into the environment. Is there any benefit in achieving aggressive maneuver? Let's call that aggressive maneuvers, right? So, and then that leads to what we call collision aware trajectory plan. So I'm listing a sketch of the controller design here, but a couple of things to note without going into every detail. The first one is we need to understand now the drone has a hybrid dynamics, right? Which means when the drone collides into the environment, you're going to see an instantaneous change of the velocity, right? It flies in, for example, 3 meters per second, and then when it bounces back, it's going to be like -1, -2, depends on what people usually call coefficient of restitution, right? So, and of course, that is a very important environment parameter that we have to identify. But we need to understand there is a hybrid dynamics. The second thing, okay, this is time optimal planning, you basically just minimize this integral. And then for those of you who remember what you learned in optimal control, what are you gonna get? You're gonna get a bump controller, right? So that's literally what we get, right? So and the difference, guys, here is you figure out whether your drone needs to do maximum force or thrust in one direction or the other direction based on where you are at the state space, right? When you solve this like simple, like a 2D problem here, what you're gonna get is you're gonna get these S and S minus and the plus in parabola, right? It's gonna be parabolas in the state space, and then that on the left side, for example, you're gonna do +1, right side do -1, vice versa, right? So, and then we can also compute the optimal time, depends on which subplane you start with, whether you start with S minus or S plus. This is the situation when there is no collision, right? This is a standard optimal time optimal control problem. Okay, so similarly, and I cited a paper here, we built a lot of our work on top of that. So similarly, you can do, planning when you know there is going to be one collision, right? So the difference is that and as you can tell from the final result of optimal time, the optimal total time for the drone to fly from A to B is a summation of two things. The first one is you have to figure out what is the time that it takes for you to fly from the initial position to the contact point. The second part is to figure out after contact, how much time it takes from that point to the destination. So this is the time from the post collision. You can see EZ is because whenever whatever the Z that you contacted to, after the contact it becomes EZ, right? You start from there and you run the time optimal control, assuming this is your starting position, right? So back then, your starting position is literally your X0. Now your starting position is your EZ, right? Because that's the immediate post-collision state. But the tricky thing is you have to figure out where do you collide, right? And then there is some derivation here, and then I will be happy to go over that offline if you have more detailed questions. But at the end of the day, guys, you still have bump controllers. It's just like the parabolas have different shapes in this case, right? I want to just give a quick illustration to help everyone understand what is really going to be the different behaviors here. Imagine this is your starting position, and you want your drone to go here. This is a simple 1D in the sense that you only have X position and X velocity. All right. So you start from here. This parabola, this right line here, is when there is no collision plan. If there's nothing in the environment you can really collide to, then your drone essentially just a phase portrait, right? This is an X and a VX. So your drone will have to just slide through this parabola, and because there's another one, when you hit this point, you basically go to another parabola and then you go here, right? So you probably do +1 for all of these and then -1 for all of these, and then you do a bump controller, and this is the final destination, and this is the time optimal trajectory you should take. What's going to happen when you know there is going to be a collision? For example, let's say if you fall here at X equal to 0.5, okay, what's going to happen is that you still start from 1 and you go with your parabola, and then you slide into different parabola. The reason why you do that instead of going this one is because you know when you get to here, that's the wall, you're going to quickly have a slide of your velocity, right? You're going to quickly turn from something like 2 all the way to -1. And that is a slide, and that happens in almost no time, right? That significantly save your time here because, and then you know at this point, you can just go back to 5 very quickly. That's just an illustration from the optimal control that we have here. And then we run experiments. Okay, so this is the experimental result. I just want to show 3 different modes, very simple task. You want the drone to go from A to B. Okay, so this is a situation when there's nothing you can really collide up. This is your starting point. This is your end point. As you know, drone is under actuated. You have to pitch in, and then you have to come back. So it takes this much time. This is the right time and starting time. Assuming you have something to collide on this side, then what you would do is you accelerate like crazy, and you use a rebound to get to the final center point. This is the right time and center. If you know there's something in between, then you collide to the side and use the collision to do what? To decelerate, right? And it quickly allows you to get to your destination. All right. So that's basically a demonstration, and we have the plot and the table here to help illustrate a little bit more. Let's assume that these are all experiment results. Assume you start from -1, 0, and you want to go to 0.30. this is what happens when there's nothing you can really collide on. And the standard optimal control that you're gonna see, basically, this is the velocity of the drone, they accelerate and decelerate, and then basically, this is the position, and then eventually it gets to point three. And then we're always looking at rise time and peak time. So I calculate this for you guys. Sorry, rise time and stopping. This is the number. Now, if you know there is a wall on the outside, and if you know that this wall has very small coefficient of restitution, which means you can, when you collide, you get no rebound, then you know you can just accelerate like crazy here. And because you know when you collide, it's gonna give you a almost a very small negative velocity, and you use that to just stop, right? And then that's what happens. Okay. And then if you have a wall in the middle, then what happens is that you accelerate, but you can see the optimal control tells you the best way to do it is not to accelerate like this part, like this, because I know this one, the coefficient of restitution is 0.4. That means it only decelerates you, but it doesn't really stop you, right? So you accelerate into an optimal velocity and use that to decelerate, right? So with that, we can see, that with collision, you can have much reduced rise time if you can collide to stop. You can have much less settling time if you can afford to collide to decelerate, right? Depends on where the obstacles are. Of course, it requires information about the environment, about where the obstacles are. But from a control standpoint, that demonstrates the capability of this drone and demonstrate how it can be integrated with optimal control. Okay, so I just want to spend some time also talking about our soft drone. Now that we're wrapping this up, we show that with this foldable quad rotor, as you can see, that we do not add any actuator here. Right, there's no actuator here, but just by allowing the collision and by probably tuning, I think Patrick was asking me the question, by just tuning the stiffness here, you can do a lot of things, right? Because by tuning the stiffness, then you can effectively also change the coefficient of restitution. And you can play with it, and then if you know the environment you're operating at, you can optimize the design, but that also becomes a co-design, co-optimization problem. A lot of exciting field, a lot of exciting things we can work on, and we're continuing looking into some of the challenges here. But a step that we are moving forward is here, yes, we have compliance, but at the end of the day, it's still largely a rigid drone, right? What if the drone's body is completely soft, right? So that goes to our design, a soft quad rotor. So I think I'm just gonna quickly show a few pictures and videos here, and then in the interest of time, the idea is fairly straightforward. Our lab has been working a lot on inflatable soft robots, primarily for wearable and healthcare applications. And there was one day that I guess my students started talking with each other. The students work on inflatable soft robots, saying, what happens if I put my inflatable stuff onto the drone and make the chassis inflatable? So basically that means it depends on how much air you pump into it, the stiffness of the chassis can be almost continuously adjusted, either online or offline as you wish. And then we're like, oh, this must be giving us a lot more compliance than the squeeze or the Explorer we have. And the answer is yes. But on the other hand, we want to explore other types of robot environment interactions, right? So far, the drones that we have shown you so far, they do not stay in that environment. They fly through and that's it. And we're like, with that additional compliance, we're thinking maybe that's something that we can use to mimic the bird and biology. Maybe we can do what? We can do perching, right? We use that compliance, we add a grasper. Can we do passive perching here? And that's what we do. We also add a grasper here. And this gripper is based on bistable mechanism or materials. A bistable material is the simplest thing we can think of is a basic sheet metal. Many of you have played with a bracelet, right? So basically you click and it curl. And then when you open it, it stays there. That's why it's called bistable. This is a stable state, and curling is another stable state. So we utilize that to basically say we release here, and then we grasp and perch. Okay, so that's the general idea. And then we submit this paper and are publishing Soft Robotics, and we're lucky to be selected as a front cover. That's actually the picture that I showed at the beginning of this talk. This shows the setup. Okay, so basically, it's basically completely fabric based. And then as you inflate, it becomes stiff and it looks similar to a regular drone. I'm not trying to hide that there are a lot of issues on that design or on that mechanism, but I want to highlight the capability, this one. And of course, my students is basically showing off how fast she can assemble the drone, right? So she basically said, I'm gonna finish assemble the drone in 30 seconds, that's short. And then apparently she took a video on that. But I think it's just to show that the setup is fairly straightforward and you can set it up fairly easily and it's ready to go. All right, so this is a drone's chassis and it flies out. Okay, so now we're just showing you the capability of the drone colliding into the environment. As you can tell, it is very easy for the drone to restabilize. We have a lot of work on recovery controller of drones, but I think this is to show that it's very easy for it to recover because of what? Because the drone contacting the environment with longer time. You can see what happens when the collision happens on the camera wheel. This is the deformation we're talking about, right? And this deformation is helping the drone to collide, to stay in contact with the environment longer. That gives you a recovery controller more time to stabilize the drone, right? If you're interested in the recovery controller, we have to talk with you more. But this is just a demonstration of the capability. We also have a video that shows the drone can perch in different objects, but I'm gonna skip that to show that autonomous perching experiment, right? So this is basically the drone flying in. This is our drone studio at ASU, and everything is autonomous. And then I'm just trying to show that the drone can basically grasp and then engage and basically perching this object, all passive through the energy from the collision. That goes back to the harness, the collision energy I'm talking about. It's all passive and it can stay there forever because it's bistable, right? And then if you want to open that, we also have a pneumatic cylinder. When you pump air, the arm will open again. And then of course, this shows that it can perch on different objects with different shapes. Right? So this is a rectangular shape. The other one is more of a cylindrical shape. And then it will stay there forever. Whenever you want to go, you basically pump air into that grasper and it will open and your drone is ready to go. Okay. And then the next part is what I really want to show, like a comparison between a soft and rigid frame. These two videos show the same bistable grasper with the same frame, same size, same weight. Okay. And you can see with a rigid frame, because of that shorter contact can be quickly rebound, it does not allow the grasper to fully engage. Well, for this one, for the soft one, because it has that flapping thing going on, and it allows the grasper to stay in contact with the perch slightly longer, and that is what tells you a success and a failure case, right? And what we're trying to show is that the compliance in the body of the drone does not only just help with collision avoidance, right? It helps with aggressive maneuvers, it helps with contact-based exploration, it helps with mapping, and it also helps with perching, right? So there's a lot of benefit. Of course, these needs to be designed very carefully and optimized. But hopefully, I convince you that there is a benefit of adding compliance into aerial robot. I don't really know how much time I have, but I really want to just also spend some time switching the gear a little bit, okay? We have seen a lot of videos on aerial robot, on robot environment interaction, but I want to sort of go to the other side of the world and look into human robot interaction. So the one that I'm going to talk about is mostly based on a NSF NRI we just completed on human vehicle and autonomous vehicle interaction. Problem statement is how to coordinate with humans who may not know you, okay? And we all have that experience. Why do you want to hang out with your friends? Because you don't have the estimator intent, right? And why it is always a little bit stressful to hang out with strangers because you don't really know what these guys are thinking. You don't know whether they like you or not. Similarly, human-robot interactions share the same problem, right? So to contextualize the problem, here's a video showing an autonomous vehicle, but it's trying to merge into the highway. Blinker is on, the car behind this vehicle is in, this car is yielding, is braking, but this car does not pick it up. And they just stop there. This car is like, okay, if you don't go, I'm brakes again. And until this guy loses patience, if you don't go, I'm gonna go, right? That's basically a good example. I'm quite sure this was a 2018 video you can see. I'm quite sure the vehicle now is getting a lot more capable. I know that there was a guest speaker from Waymo a few weeks ago. And then actually Waymo is running a lot of testing in Phoenix, right? They have these vehicles running right in front of my house, and they also start testing on the highway. Capability is definitely improved, but I hope this gives you the context of what we mean by interacting with another agent who does not really know you, right? Apparently, it turned on the blinker, but the information in that blinker is too little. It does not tell the car that do I want to yield or do I want to go first, right? That's a simple question, but it doesn't contain that information. So that results in that low efficiency in that interaction. Luckily, there was no accident, but you can easily imagine an accident happening. Okay, so motivated by this problem, we started looking at how can we really formulate this as a game theory problem, right? That looks into human-robot interaction. So I think this, again, is a sketch of what we did. The problem formulation is really to look into, okay, let's assume you have a human vehicle and you have an autonomous vehicle that is interacting in an uncontrolled intersection. There's no traffic light, they have to figure out who to go first, okay? Let's also skip the stop sign a little bit, right? Let's just say they can go wherever they want to go. We model both the human and the robot using this utility function or like cost function, all right? So basically there is a safety cost, which means you don't want to get too close to the other car. There's also a task cost that you want to eventually cross the intersection and you want to cross ASAP, right? So, and we generally formulate, this sort of human-robot interaction, especially with, this hiding parameter as incomplete information differential gain, right? So the idea is that each agent has that theta I, as you can tell, that plays a critical role in helping each agent really figure out what will be their action. But this parameter is unknown, right? Because you don't, and then we basically describe this as aggressiveness, okay? Apparently, the higher this one is, the more aggressive you are, right? And then certainly, different human drivers have different aggressiveness. And I'm quite sure everybody's aggressiveness varies, depends on whether you're in a rush or not, or whether you're in a good mood or not, right? That changes all the time. But clearly, that's not really something you can just put in front of my car saying, I'm not aggressive, right? You can't really do that. So then how can that, dynamic negotiation happen between the human and the robot? Right? So this is the cost, and then we basically say this is instantaneous loss, this is accumulative loss over a period of time. And then we basically look into the baseline Nash equilibrium. There are a lot of different versions of the Nash equilibrium here. It depends on what are your assumptions, right? It depends on how you assume each agent solved the game, right? Depends on how they solve, because there is an incomplete information here. They can solve that in different ways. Here I'm showing you the baseline version. Okay, the baseline version is this. The Nash equilibrium is here. Basically, this zeta is your control input. Okay, it's UI. It's basically UI for this is the U for ego vehicle, and this is the U for the other vehicle. So essentially, to solve a Nash equilibrium solution, what the ego agent needs to do is basically minimize this cost. But what I want to highlight is that the cost is certainly, dependent on its own action, zeta I here, right? But it's also dependent on what? Dependent certainly on its own parameter, but it's also dependent on what the ego agent thinks the other vehicle will do, right? But in the ego agent's mind, how do they really estimate that? That's really the difference. You can have multiple different ways of estimating what the other vehicle would like to do, right? The baseline is you assume the other vehicle will just minimize their own cost function, assuming they know what you will do, right? For example, if we run that in a temporal fashion, that is to say, if I give a optimal action here, then the other vehicle, we assume they know what I'm doing, right? And or they know, or we assume you have direct observation of my control input. And that is basically what we call that, okay, essentially the other vehicle is really not doing it's not doing any intent inference. The other agent is not doing any estimation. We assume the other agent knows everything, right? So, but as you can tell, there will be problems here, and I will also share with you like the different formulations of the Nash equilibrium and the intent inference. But this set the baseline, and then just so you know what what Nash equilibrium is in this problem. For motion planning, right? So we look into multiple different motion planners. Depends on what is our assumption on the other agent. Because in whatever we do, we have reactive motion planner, proactive motion planner, and courteous motion planner. There are a lot of details here, but the main difference is here. When we estimate, right? When we estimate the cost, what is our assumption of U, right? In the reactive motion planner, I assume that your action is based off some offline calculated probability distribution. We have past interactions. We know that typically how you do it, and we basically just sample from that distribution, right? So that's why we say plan based on your action. The proactive motion planner is to look into this conditional probability, right? Instead of looking at this marginal probability, I look at the conditional probability. The conditional probability is I consider how I might influence your actions when I design mine, right? That's why we basically say the P of zeta, this zeta they had dependent on zeta I, right? That is to say, I do know your action is gonna depend on mine, so I leverage that and be what we call proactive. Right. The last one is the Curtis motion. I want to acknowledge that this is not really something that we proposed first. We built on other people's work, but the main difference is that we basically calculate the courtesy loss by looking into what we call the rational courtesy loss. Okay, there's a lot of details here. Generally speaking, the courtesy loss is basically to calculate what will be the loss for you and what will be the loss when for your best scenario, right? What will be the loss if I take certain actions versus what will be the loss if I do whatever I can to minimize yours, right? And then whatever the difference is, that's the courtesy loss. That means I make you lose more, right? By taking certain action. Of course, if that loss is zero, that means I'm perfectly courteous, right? But the difference between how we define courteous motion and the previous work is that we basically define that courteous motion based on what we call the Nash equilibrium set, which is to say, when I calculate how I do things and how you do things, I only pick up from the Nash equilibrium set. I do not really go out of my way to please you. There is a Nash equilibrium solution of my action and your action based on different initial conditions. I only sample from there instead of sampling from the entire action space. Right? So that's the main difference between what we say rational courtesy loss and then just the regular courtesy loss. And we will also show you some results based on different definitions. Okay, so this is a page that I really want everybody to take home with. Okay, so we have a lot of problem statement in the previous page, but what I really want to highlight is the difference between what we call non-empathetic intent inference and empathetic intent inference. Right, the main difference is shown here. Okay, let's assume that, as you can tell, the human and the robot can either be aggressive or non-aggressive, right? Based on our definition. There is a theta there, whether they are like high or low, and certainly you can make that continuous, but we're simplifying that into you can either be very aggressive or very non-aggressive. So the probability, let's assume this is your probability. A non-empathetic agent will basically run this parameter estimate, assuming the other agent knows what my true aggressiveness is. For example, in this case, for a robot, because the robot knows that I am non-aggressive, then it will basically only look at this row to see between these two numbers, which one is higher. And in this particular case, human being aggressive is more likely. So basically the result for non-empathetic intent inference is that, oh, maybe I am not aggressive, you are aggressive, because I think you know I'm not aggressive. Well, the empathetic intent inference, in simple word, is basically just to perform a joint probability, right? Instead of looking at conditional probability or marginal probability, right? In this case, I look at all of these because I know, although I am not aggressive, but you might think I am aggressive, right? And in this case, we realize, okay, that's actually more likely, right? The most likely scenario is I am non-aggressive, but you think I am aggressive and you are actually non-aggressive, right? And as you know, this sort of cognitive propagation can go a level higher, right? Now I'm looking at your intent and your estimate of my intent, but it can go a level higher, right? It can go my intent, my estimate of your intent, of my intent of estimating of your intent. It can go forever, right? But certainly, you know, we realize that probably one level estimation is oftentimes enough, right? So, but hopefully this quick table shows you the difference between different estimation of intent and also how we make decisions. Right? It's just to really think about, does the other person know me or not? Right? You just basically consider the fact that the other person may not know you. That's what empathy really means. Okay. And at this point, I kind of forgot why I named that empathy, not empathy. But I think the reason is I need to be empathetic about the fact that you don't know. All right. So I want to very quickly show some like follow-up work we did. This is a work that was in ICRA 21. What we have done here is that we also look into the human decision models, right? So up until this point, our human decision has been pretty much point decision. Okay, so I estimate you are aggressive, you are not aggressive, and basically that's your label. You're either aggressive or not aggressive. But certainly there's a probability going on. So, and we look into the literature of bounded irrational human models or noisy rational human models. For those of you that are familiar with that, it's actually a very neat model that's just to say that, okay, so you will most likely choosing actions that are optimal, but there is a distribution here, right? Essentially, that's why right now we have two parameters to estimate. One is a reward parameter and the other one is a noise parameter. Essentially, the more noisy you are, the higher that lambda is. That means your action can be more distributed, right? Centered around the optimal line. And then we also have some follow-up work on this to challenge this assumption, but I don't have time to talk about that. But I think this is kind of like our next step towards like a point estimate that you're aggressive or not aggressive. But as you can see, when you introduce those things into a game theoretical formulation, solving that problem becomes very hard, right? Because it's a massive game. You have a decision layer, but you also have the intent layer, right? So, and what we do here, and then this is our game differential game formulation. Again, I have to go through this fairly quickly, but happy to, I mean, more details are in the paper, but I'll also be happy to share more about it. The problems formulation is that you have this, value function here, right? So optimal control problem, you have the value function here. It's basically a final loss, and this is an instantaneous loss, and you basically do an integral of that, right? For those who are familiar with optimal control, this is standard one. And then basically our instantaneous loss is again, basically your control input and the collision loss. And here we model the collision loss. Here's a graph. It's just to show that when you're aggressive, your collision loss is actually a lot lower in these regions when the aggressive loss is already high, right? Which means for aggressive agent, I only consider my safety loss being high in a very small region because I'm aggressive, right? So, and you also have a final loss to incentivize speed killing. This has become a interesting differential game problem that we can resolve to optimal control. I'm going to quickly skip through our way of doing that. Essentially, for solving differential game, you start with Hamilton-Jacobi Essex equation, HAI equation, right? You start with HAI, and then you basically define the Hamiltonian and you find the optimal control. This is the Hamiltonian here, and this is basically the value function, and this is the dynamics, right? So, and then we solve the HAI equation by formulating the problem into a bounded value problem, BVP problem, and you solve that using PMP. Basically, you have the state involvement, the co-state involvement, and basically you solve that by minimizing, or in this case, maximizing the Hamiltonian. Okay. So, and then what we are doing here, guys, is that by solving all these problems, as you know, right now we're solving an optimal control differential game at a fairly large state space, right? And as for those of you that are familiar with it, solving this is very computationally intensive. You probably can't really afford solving this online. But what we're doing here is that we're basically solving these games offline with different initial conditions. And then we basically collect a data set from the BVP solver that would basically tell you with different initial conditions, you can see there's a different state, different time, different data parameters. And this is our neural network weight. What we're trying to do is to use the neural network to fit the value, right? So we basically create a new value network, right? And then we basically train that value network using the data we have solving from PMP, okay? And with the trained network, then you can easily get the Q function, and that will allow us to maximize or allow you to make decisions very fast, right? So that's the idea here. So very quickly showing some animation here, you can see the difference, right? So basically in that paper, what we're really trying to figure out is that when you have either the correct or incorrect belief of the other agent's hidden parameters, do you really have any benefit of being empathetic, right? When you're intending inference of decision making. And then here, what we're trying to show is that there is, right? Because when with the same initial condition, my car slows down much earlier, and there is a much larger space the other car crosses, right? Even if I have the incorrect initial belief, which is to say, this agent is aggressive, which means he wants to go first, but initially I don't know that, right? And you have to run this belief network and then also decision network to basically get that done. And then we're showing you the same initial condition. This one stops at a much closer one, and then as you can see, it's almost flying. And similarly, the reverse part is that if you're a non-aggressive agent, but you assume they are aggressive, you have similar results, right? And then again, and the one here is to show you that at that point, we can estimate the other's intent parameter correctly, right? And in this case, you can see with non-empathetic, they never really figure out what the other's aggressiveness really is, right? So it basically makes the decision in a fairly wrong fashion. It doesn't mean that it always collides, but as you can tell, there is a risk. This is another figure that I think that probably takes a little bit of time to fully explain, but I think what I was trying to show you is this. This is the figure that shows what happens when you have the correct initial belief of each other's aggressiveness, and this is what happens when you have incorrect initial belief. Okay, let's start with the correct one. So here in this one, for example, when we have EE, that just means both agents are empathetic when they're running intent inference and decision. And then this theta star is telling you what their true aggressiveness is. This is to say both agents are not aggressive and both agents are running empathetic intent inference, right? And in that case, what we're trying to show you, this is kind of like the effective position of the car. And what we're trying to show you is that the car usually starts from here, and this is kind of like what we call the bender zone. This is actually the intersection. And what we want is your trajectory not to cross here. Does it make sense? If it crosses here, that means your cars are being too close, right? And then with that method being said, in short, you can see whenever you're running empathetic intent inference, there's always a benefit, right? There's always a benefit, right? So your car cross that intersection much less frequently or much less likely, and that benefit is also clear when you have incorrect initial belief. Well, of course, there are situations you still cross it and say no, but we're just trying to show you that running that empathetic intent inference is beneficial, right? And whether you know the other is true intent or not at the beginning. Okay. This is probably the last page that I want to show about this topic, and this is to go back to the courtesy thing that we talk about when we do planning. Right? So this is to say that we have different planners, right? So we have three. This is basically both the proposed and the benchmark. The benchmark, I think if you remember, the benchmark courtesy planner is one I basically just be encouraged no matter what. Right? We do not do what we call the rational courtesy. So in this case, what we're trying to show you is that if the autonomous vehicle, if the autonomous vehicle is far away from the intersection to start with, right? No matter what you do, it will always deal with the other thing, right? Because I'm far away, and in order to be courteous, of course, I want you to go. The difference is really when I am here, but you're far away. The difference is that the benchmark courtesy that, okay, if I want to minimize your cost, I need to do whatever I can to please you. Of course, the best way to please you is to let you go first. Although I'm kind of close at the intersection, I'm going to brake and stop and stay there for 5 seconds, let you go first. And then the difference here we're showing you here that with our definition of courtesy, what we call rational courtesy, which means I choose action from my equilibrium set, then I know because I'm close to the starting point, the best action is for me to go first. Because even if I go first, I know you're gonna not encounter high courtesy level, right? Because letting you go first is not really an equilibrium situation, right? So that's the difference between the courtesy and our different definitions. Now, here we're just showing you the different ways of courtesy laws. I think we can kind of escape that. It's just to say that when you put higher or lower weight on courtesy, the vehicle will become more or less courteous. Okay, so that's kind of just a quick summary of this page. So this work was led by my former student Yue Wang, and also in collaboration with my colleague Professor Max Zhang. Okay, so I think that's pretty much what I have today. I want to spend a few minutes to just summarize all the things that I talk about, and hopefully help inspire some discussions. We show that in robot environment interaction, putting compliance into the aero robot design enable a lot of new locomotion modes, including traversing complex environment, include contact-based navigation and mapping, and include collision resilience and friction, right? And on the human robot interaction side, we show you the challenge of dynamic negotiation between a human and robot agent. And we formulate that as an incomplete information dynamic game, or more specific, incomplete information differential game. And we basically introduce the concept of empathetic intent. So for future work, my first step is always to look into how can we better model the interaction, both on the human robot side and robot environment side. And then our modeling is focused on two questions. One is how to handle the unknowns that the interactions you have never seen before. For example, I have the drone that have aerial robot contact, but probably this is a wall that I know, but tomorrow I might fly into an environment that I don't really know the environment. I don't know the coefficient of restitution. What should I do, right? Also, it's handling the uncertainties. And I'm showing you an example here. This is what we're talking about. That's why we're start to challenge that bounded or noisy rational human models. You probably will assume that the human is making some sort of noisy optimal decision, but when accident happens, that's when people are doing this, right? They're not making any optimal decision whatsoever. Then how can you really understand somebody is doing things in this way, and you quickly update your human models, right? That's the and that's basically the two things I'm talking about. So on the robot environment interaction, we recently spent a lot of work looking into contact models, hybrid system modeling to model the state jump, right? And then the next thing, once we have better model of the interaction, is to, I think what is a very important question for interactive robotics relative skill up decision making. So that also has two different aspects. The first one is relatively simple. That is, everything that I talk about is one-on-one interaction. You have one robot interact with one environment. You have one robot that interacts with one human, right? But what if you have more robots or more humans, right? This is a very natural questions to ask, because you can probably create scenarios when there's a one-on-one, but oftentimes you have more robots or humans around. How can you really make decisions? The other one is really to look into how do you really balance computation and performance, right? For example, for these sort of aerial robot, you probably cannot really afford having like 10 GPUs on top of it, running crazy computer vision algorithm there, everything done. And so then how do you really balance that trade-off, right? That trade-off is certainly different. You can probably afford a little bit more on autonomous vehicles, a little bit less on aerial vehicles. But I think there is a need for us to look into the general design guidelines, into how that balance can be done. And then, of course, in terms of decision making, what is very important that I didn't get a chance to talk about is how can I really get formal performance guarantee, right, of such interactions. Right now, everything works, right? I can also find another 1,000 videos that none of these works, right? I'm certainly showing you the cool stuff, right? Because I'm an invited speaker, I want to make myself look good. But on the other hand, then the question is, how can you really have these performance guarantees, and how can you even predict things are gonna fail, right? That goes for verification, validation, robustness, safety, and all this stuff, all this cool stuff that folks are working on here. We're very much looking forward to having some discussion and see how we can jointly together getting these interactive robots more reliable and deployable. Lastly, is testing in real world. I'm showing you two examples of what we mean by here. This is what the real world of aerial robots when they're actually doing search and rescue, right? That's what we're talking about, right? You can have crazy computer vision algorithm, but you can't really see anything, right? You can have all my nice range estimation algorithm, but the IMU may be faulty, right? So how can you really allow autonomous operations here? This is traffic, right? So I can have maybe one of my vehicle here, but I think it's just a matter of time. I'm going to collide into something, right? Because of the reason I talked about, I didn't scale that up. We have, I don't know, 100 people here, right? So then how can you really get that done, right? So there are a lot of work that needs to be done. And I think including perception, including planning, including understanding the contact, understanding the human, of course, we have to do feedback, right? So we have to feedback, and that's the most important thing we learn as controls engineers, right? You always learn from the measurement in real world and go back and see how you can make the model better, make the control better, make the planning better, make perception better, right? So I think that's all I have today. I just want to acknowledge my lab, either the students that I talk about their projects or students that I didn't get a chance. I think they have been doing a lot of exciting work, and also my funding sources. I'm going to leave these GIFs here while I take questions. Thank you for your time.
Open up for a few questions from audience. Anyone started? Yeah, here.
I've always been really interested in the courtesy and the empathetic kind of nature, your approach to thinking about using those to guide sort of how you're thinking about that interaction. And I don't know if you've said this before, but you made a comment about sort of remembering why you guys started to use the term empathetic. I guess I was curious if that if any of that is grounded in social science literature, or it's really just your intuitive life is going to be empathetic.
That's
A little bit more firm grounding.
That's a great question. So I think there is like backup in social science that we look into, and then also there is that level K cognitive theory. I'm quite sure you're also familiar with. That is really just to say how many iterations do I go in that cognitive chain. And then generally speaking, the social science is telling us that most of the time human performs this sort of like empathetic intent inference when they're in a competitive setting. For example, when you're playing poker game, right? That's when you, as a human, run empathetic intent inference because you want to figure out how your competitor think of you, and so you can win the game, right? But on the other hand, the literature tells us generally in a cooperative setting, or when the human are not trying to be adversarial, they generally just perform one level, which is they typically call that level 0, which is to say they just estimate the intent. But the proposal is that we as the robot needs to basically model that intent inference process so we can leverage. So the robot becomes level 1. So similarly, if the human is told that this is a competitive game with the autonomous vehicle, then naturally human will be level 1, then robot needs to be level 2, right? If you want to really like make sure you can coordinate with someone else that don't have control with, you have to be one level higher. So that's what we learned. That, but of course, I think to address the questions, there is still a lot of questions we need to answer about, like are human really estimating the autonomous vehicles intent? So we also have some other work that looks into what we call event-driven intent inference. That is to say, I do not continuously run that empathetic intent inference. I only estimate my intent when I realize even empathetic intent inference, my previous intent inference cannot explain your behavior anymore. It's just similar to event-driven control, right? Event-driven control is like, I basically just only design or put control actions when I realize the error is too large. It's a similar thing. So we have another paper, we show that by running that, we do not sacrifice safety, but we significantly reduce computation time because you only need to run intent inference once, when the human changes their intent, right? So I think that's something we're doing. And also, I think there is also a lot of work needed to really look into exactly the question you asked, right? HRI is a very broad field that different interaction, different tasks, sometimes depends on how you instruct the human, right? The human's I know there are a lot of work you're doing in your lab related to trust. I think that's also connected, right? Depends on how you instruct the human is gonna do things different, right? So I think there is also that factor that oftentimes is overlooked. And I think it's also important, right? Because if you tell the human to be more careful about what the robot is, then the human is more likely to estimate the robot time, right? And otherwise, the human will do whatever they do, right? So I think that's also.
Fascinating.
Yeah, thank you. Thanks for the question. Yes.
Thank you for a great job. Something new and that's something interesting. So I had a question regarding when, instead of a human and an agent, there are multiple agents interacting, and we have a very good sense of what the other robots are doing because they're of the same team. In that scenario, is there? I think it follows from the question that was posed. In that scenario, do we need to have? Is it advantageous to do a game theoretic framework where you predict what the other is trying to do, or go with a normal, a classical control framework where
I think that's a fascinating question. I think also somewhat connected to Dr. Zhang's question. I think one part of the answer that I have is, it really depends on the setup. It depends on what type of task is being given to that human-robot interaction team, right? It also depends on what are things that you have told everybody a priori, right? If you have basically laid the ground and tells everybody that's what everybody should do, then I see there's certainly a last need of running this sort of empathetic inference. The reason why we're doing that for autonomous vehicle is also because autonomous vehicle is also an application that you have very limited ways of transforming information, right? Because other than blinker and then actually just drive, there's nothing you can do. You can't really shout at the other driver saying, I want to go first. Or even if you shout, the autonomous vehicle won't understand, right? So that belongs to one of these applications that you really have to be careful about. The other person may not really know what you're trying to do. But there are other scenarios when you can use language to communicate your intent, right? That's why I think there are a lot of people in the HRI community working on large language models and using language to facilitate intent signaling and intent estimate. So that's another way to alleviate the computational challenges for what I'm talking about. But there, of course, you can also think of adversarial settings, right? That you have a robot and there are a lot of adversarials that you can't really convince them to be friendly, right? Then you have to continue running this with them until somebody wins, right? So another thing that I want to sort of mention, another perspective is really the one that I talked about, the performance versus computation aspect, right? Ultimately, the reason why you have that question is because running that with multiple robots and multiple humans are expensive, right? So ultimately, it becomes a trade-off of how good the performance is. I showed you guys, right? Even if I know your true intent at the beginning, running empathetic intent inference is still beneficial. Right? So there's always a benefit there, but then how to quantify that benefit, that's actually, in fact, one of the things we're working on right now. How do we really quantify that benefit? And do we do that outweigh the significant increase in computational challenge or computational cost? So that's certainly the trade-off that we need to balance, as what I was saying here. And of course, that depends on how much computational resource you have, how frequent do you need to make decisions, how many agents are there, and there are a lot of factors that will determine the answer. So unfortunately, I do not have an answer of should you go A or B. I think it's really case. Does it help? Yes.
Okay, yes, I have a question that goes off from that. So how would all of this modeling be simpler? Like, we just assume every car will be autonomous, like, it would be just a robot, let's say, I don't know, like 5 years from now, like, would all the modeling just be simpler if we assume everyone has the same setting on courtesy and all of this?
Okay, so that, I think the answer is going to go a little beyond my paycheck. But I think what I would like to say is that I think in the foreseeable future, it's very difficult for you to convince each company that are building autonomous vehicles to fully communicate how they run their algorithm. And it's very difficult for you to say, okay, I have the unified standard of running autonomous vehicle, and everybody has to do their decision making in the way that, for example, I propose, right? Because that doesn't seem like something that you can really, regulate, right? So I think that's one. The other one is that even if everyone is autonomous, but you still have these interactions. These autonomous vehicles will interact with pedestrians, right? You still have this human-robot interaction. It's just like at that time, it's not a vehicle anymore. It's a pedestrian. But we also have some work actually in that paper that looks into how do we really consider the different vehicle dynamics, right? Because some vehicle can decelerate and accelerate much faster and less. And then how do we also incorporate that? We also have that dynamics-aware motion planning in there. But similar, that can be a human because human cannot really accelerate this part very fast, right? So I guess my point is that I think what you mentioned is definitely the future when you have more autonomous vehicles on the road, especially when the infrastructure is more advanced. You can have V2V communication or V2I communication that allows better coordination and less misunderstanding. But I think that human-robot interaction, even just in transportation system, will still be there, right? Even if, let's say, the autonomous vehicles on the road, we also have a lot of issues, for example, social navigation. I think we were talking with many colleagues here today about social navigation, right? You have all these food delivery robots, right? You don't want them to behave aggressively on campus, right? And I think in the future we might see a lot of robot dogs. I see a lot of robot dogs today visiting different labs. They might also run on campus. You also want to make sure these guys are also courteous, right? There are a lot of questions that will emerge. I think the problem will still be there. The application might be slightly different. And then certainly there are work that needs to be done to fit in these. Next. Oh. Okay.
I know there's a lot of pretty complicated. Body dynamics and also the efficiency in the topic flow, timing, and also location. So, are you going to use space approaches or also exploring
Sure. Right. So I think that's certainly that's a great question. It's a $1 million question, and I'm gonna give a 5 cents answer. Okay. So I think I think for that particular contact models, right? I think there is. Let me put it. I think there's a trade-off that we need to make. For example, I'm not gonna start with that. I just want to be honest with everybody. I'm not going to start with that. It's just because there are too many things that you have to incorporate in that model, exactly as what Professor Hu just mentioned. You have this sort of curve in here. You can see it, right? You have the pneumatics, you have the material compliance here and there. So I think certainly that's not something we're going to start with. I think the content model we're going to start with is probably mostly on these drones that have a little bit less compliance, but also, resemble the challenge. I think some of the things we're looking into is there is a lot of work in contact models, particularly looking at model the contact as a linear complementary system, LCP and LCS. So we're looking into that and specifically how do you really solve the LCP problem more efficiently. And there are a lot of work related to use of, for example, physics informed neural network, right, into solving LCP. There are also people using, for example, PIN just to model the contact directly. But literature has shown that when you have sharp change in your system state because of the large gradient, and oftentimes neural network does not really work very well in these scenarios. So I think that's why I kind of like, for example, that LCP idea, that is you model the contact as a physics-based contact, right? But you solve the problem using a data-driven approach. I think that's one of the directions we're looking into. And I hope in a few years I can come back and tell you what we have at the time. Yeah. So, but I think certainly, as we discussed earlier, I think, for example, for modeling this type of contact, there are a lot of things we can learn from the locomotion community, working on biped locomotion, because we share similar problems in the sense that you have a robot that contact the environment and it resulted in a hybrid. I think for you guys, the hybrid zero dynamics, right? So, and in our case, it's also a hybrid dynamics as I've shown here. And I think there are a lot of things we can kind of learn and by looking into what the locomotion community is. Yeah.
Oh, that's good question. I think maybe the contact right phenomenon is really interesting here, but then you have to think another way. All these models are abstractions for certain purposes, especially contact. Okay. Contact, if from system level, it occurs really fast. Then the best model is not like discontinuous, or just I'm just either making the contact or I'm bouncing off. Right. So yeah, this type of thing, obviously, then you got to data-driven neural network too sensitive to the context. Right. There's no way you can do it well. You're right. But on the other hand, if my system, I'm humanoid, can react really fast, then the contact, in a way, I'm able to control the interaction are there compared to the online data. It's not fast. Then now, then this kind of instantly one is not a good model. That's there I can even open up the physical based, right, and to deal with. So from my point of view, really when we talk about the content model, it's really you're looking at what type of system we're talking about, what abstraction we're going to have. Exactly. Yeah. So yeah, that's where I'm coming from. That's where I see maybe bring out the issue, just say why and see when the people are talking about controls, just to get rid of frequency to me model. And see the analysis of the garbage to see. Without frequency modeling, you don't understand what time scale I'm talking about. Right. When I'm going to model that as an instant jump, and when I'm going to continue have use a continuous model to do things. Right. I think you raise an excellent point. This is also something we encounter when we're looking into modeling the drone or contact the environment. I think it really ultimately gets at how fast you can really sample. If you can sample at 1,000,000 hertz, then everything is continuous. Right? Then everything is continuous, right? And then when you look at the gradient is super small, you're okay, you can use a neural network. The challenge is that you can neither sample this fast nor control this fast. So that's the trade-off. That's why you have to use discrete or discontinuous models, because the last sample you are here and the next sample you are here, right? So that's the gradient you are looking. That's all you can have, right? So I think I couldn't agree with your point more. That is, it's ultimately a joint decision between, of course, the task you're looking at, but also at how fast you sample, how fast you control, what is really the objective, and what is really kind of like the abstract, right? So that we can look into the best model, right? So that's why I think we have been looking in the literature. People have shown that the generic neural network, deep neural network models works better when the stiffness of the wall
is lower. And then you can easily understand why is that. It's because when this is lower, the contact time is longer, and then the change is less sharp, gradient is smaller, your neural network works better. Right? And on the other hand, what is a rigid to rigid contact is the hardest. I think if you guys are interested, I can send you the paper from a group that shows that that's the worst. When you have a rigid drone colliding into a rigid wall, you probably don't want to do that, right? Anyways, but I think that's the worst. And then the reason is because the rebound is fast, and you can only afford one sample, and that's it. Right? That's why we're getting a little bit more hopeful if we have a more compliant drone interacting with a less rigid surface, we might be able to leverage, let's say the LTP. LTP is ultimately a discrete model, but I think we can leverage more continuous version of neural network models. And I think that goes back to what Professor Yao said, right? That it really depends on how many data points you have for the contact, right? So, and unfortunately, that goes back to my computation performance thing. The drone, you can't sample at a million hertz, so that's why you have to take that trade. Thanks for questions.
We'll probably take one last question.
Okay.
So we can hear me talk,
Sure, definitely.
but just related to what John's point was, in terms of like future direction.
Right.
If you mentioned that with the inflated drone, how hard it is was it? Even with not thinking about this,
Okay.
in terms of level of pressure. I guess we didn't.
Mhm,
But
mhm.
and tested on the pressure and easier than all the activation.
Exactly. Exactly. Yeah. So I think that's a very good question. I think when you ask that question, I was thinking in my head, how do we really quantify how easy it is to control? Unfortunately, I can't really think of a metric to say, okay, how easy it is. But I generally agree with you that you have to do more. For example, if you use a PID controller, you certainly have to do more tuning in there. And I think that goes back to our question that we don't have a model that is very good for that, right? And that model has strong uncertainties. And then also, I'm not trying to, I think I can tell you that this thing is leaking. This thing is leaking at a very small rate, right? But it is leaking, right? If you let it fly for a year, I think this one would die, right? So, but then how do you really describe that? That's why it goes back to my deploy to the well, to the field, right? When you deploy to the field, you can't say, I just want to perform a demo and be done, right? It has to be there for a while. So certainly, I think my point for this one to control is, I think it's to still start from models, how you really build models. Certainly, I think that's why I said I probably don't want to start from that, because we don't even have a good model of the drone itself, right? And then I think many of you have seen that little bubbling here, and that is because it's soft, right? And there is that, and then also going back to the frequency question, right? And if you don't design, or if you pressurize that into a certain state, it's gonna resonate. Yeah. Right? So, and it depends on, and then that resonance is very hard to be predicted because you can't really a priori set your propeller speed. Right? And then the moment you're trying to pivot to pitch, and all of a sudden that thing start vibrating because you change the motor speed, right? So I think there are a lot of things that we need to look into, but I guess I think I told my students this as well. I think in order for you to be a good controls engineer, you need to spend 80% of your time doing models. Yeah. The reason why you spend so much time on your controller is because your model is not good, right? So you have to do robust, you have to do adaptive, you have to do this and do that. Or if you have a poor model, then you get back to the PID, right? But there's not much information that you basically just kind of do. So I think it's another field. That's why we're doing PID, right? Because we don't know, and then I would be more than glad to talk with folks here at Purdue who have interest in working with SAS and building models for this point, right? So but I agree with you, Patrick, that that's just definitely a control challenge, and it doesn't really take us a lot of time to get it to work, and that is because we can make the breathe fit, and then it goes closer to the dynamics of the regulation. But I agree with you. We haven't tried like very low pressure like 5 psi. I think we can barely take off, but certainly there are more challenges in between.
All right, thank you, Wenlong. I noticed your lab has a Twitter account, YouTube account, so hopefully you'll get 20 more subscribers after.
Well, you see, that's the reason why I put them there. I didn't even know this. called X, right?
Yeah,
So,
thank you for flying from Phoenix all the way here and sorry for the bad weather, but over the weekend it's gonna be warmer. But thank you. Let's thank. Everyone, enjoy the weekend.